Hi guys, in this lecture we will continue from where we left off and we will look at some more type of problems that can be asked based on synchronous machines. So last time we looked at parallel operation, so this is one more type of problem that can be asked on parallel operation. Usually when alternators are connected in parallel, the purpose behind that is to supply higher value of load. So the alternators will generate a total power which is equal to the load power. But here we are neglecting any losses in the transmission, which means apparent power or sum of apparent power of generators should be equal to sum of apparent demand. Okay, and as you can see I have placed the phasor sign above, which means they shall be added as phasors, or you can say their real and imaginary parts will be individually added like this. Summation of real power generated is equal to real power demand, and summation of reactive power generated is equal to reactive power demand. While taking reactive power, keep in mind the concept of lagging and leading. Usually for lagging, reactive power is positive, for leading it is negative. Okay, but in real power there is no problem of sign. Generated power is always positive and demand is negative. So let us see the problem that we have been given. Two 550 kVA alternators operate in parallel to supply the following loads. So these two are the loads. So this basically is demand 1, demand 2. One machine is supplying, this is the supplied power, so PG1. We need to find the power factor of other machine. Now one thing I know is there are two generators, so total generated real power should be equal to total demand real power. Total generated real power is how much? 200 plus PG2. Total real demand power 250 plus 100, which means PG2 is 150 kilowatt. Now in order to determine the power factor, we must also have the knowledge about the reactive power. So first we should derive the reactive power for first load, that is QD1. As you can see, it is lagging power factor, so reactive power shall be positive. We know reactive power is given like this, P into tan of phi, and power factor is cos of phi. So I can determine phi by taking cos inverse of power factor. So QD1 I am directly writing 250 into tan, and phi will be cos inverse power factor is 0.6. Okay. Similarly, QD2, it is leading, so it shall be taken as negative, minus 100 tan cos inverse 0.5. Similarly, QG1, it is lagging, so it shall be positive, 200 tan of cos inverse 0.9. Now we know QG2 will be equal to QD1 plus QD2 minus QG1. If you do this, you will figure out that QG2 will come out to be 63.26 kVAR. Now we have real power of generator 2 as well as the reactive power. So we can figure out the power factor angle phi. It is QG2 by PG2. It is actually tan of phi 2. Similarly, if you want to find out cos of phi 2, it will be cos of tan inverse QG2 by PG2. QG2 is 63.26, PG2 is 150. So from here it comes out to be 0.92. But now whether it is lagging or leading, as you can see reactive power is positive, so it should be lagging. So that is how we can derive the power factor of any machine when we talk about the parallel operation. Is it fine? Moving forward, the next type of problem that can be asked is based on efficiency and losses inside the synchronous machine. So before finding efficiency of any machine, what you need to remember is power flow. How does the power flow inside a machine? So first, if we talk about generator, in generator we have shaft input and we have input at the field. This shaft input causes rotational loss and then it is converted to developed power. Now what is developed power? EF IA cos of psi. What is this psi? It is the internal power factor angle or the angle between induced EMF and current. It is not equal to power factor angle because power factor angle is the angle between terminal voltage and armature current. It is between induced EMF and armature current. Then we have copper loss and then we have output power. Now what is this rotational loss? It is actually equal to friction and windage loss plus core loss. So remember this field power. So whatever is the real power in the field is actually taken as a loss. Why is it taken as a loss? Because the function of field winding is to generate the flux which should require only reactive power. So whatever is the real power consumed in the field winding, that makes no use and hence it is taken as losses. Similarly for the motor, how shall we draw the power flow diagram? For motor we will have electrical input, we will have field input. After electrical input we will have copper loss which will lead to the developed power. Again it is same, EF IA cos of psi. Then we will have rotational loss and then we will have shaft power. Okay, so entire power flow diagram is just reversed. Now let us see the problem that is given to us. It is saying a 150 kVA. So that should be our output power or output rating, because in kVA only the apparent power can be given and mechanical power does not have any imaginary term, so it is electrical power, and for an alternator electrical power is the output power. And also remember, do not directly use rating in any equation unless otherwise you are given full load, half load, quarter load, because these loads are in comparison or in reference to the full load or the rated power. But if you are given certain load power, you have to use that as a load, then rating will not be used in the problem. Now if you see, we have friction and windage loss and the core loss. These two will combinedly be called as rotational loss, so that is 850 watt. We have field winding resistance, we have field winding voltage. Now we know in the field winding we have DC supply. So what is the field loss? Field winding voltage square by field winding resistance. So this is 375 watt. We need to find the alternator efficiency at 0.8 power factor and half of the full load. Now let me calculate full load current, which is actually rated current. 150 kVA, so 150 into 10 to the power 3. Now remember, this is apparent power, so there is no need to use the power factor. I can directly use S is equal to root 3 VL IL. And since it is star connected, IL will be same as the phase current. Okay. But if this power was real, then we will use P is equal to root 3 VLIL cos phi. So this is a very common mistake. We do not consider that either the power is S or P. We directly use it. Is it fine? Root 3 into 500. So this current shall come out to be 86.6 ampere. Now this current shall be taken as half. So sorry, this will come out to be 86.6. Why I am taking half? Because it is I half load. Okay. Now this current will cause copper losses. So what will be copper losses? 3 Ia square Ra. Remember this factor of 3 because it is a 3-phase machine. 3 into 86.6 square into RA is how much? 0.03. So this comes out to be how much? 675. This is actually 312.5. Now we have all the losses. Let us calculate output. Output is given as half of the full load, which means 75 kVA. And at 0.8 power factor, so P is equal to S cos phi. So how much will this come out to be? It will come out to be 60 kilowatt. We have output, we have losses. We can calculate efficiency. How? Output by output plus loss. Loss is 850 is rotational loss. 312.5 is core loss, sorry, field loss, and then 675 is the copper loss. So this will come out to be 0.97, or you can say 97%. So that will be the percentage efficiency of the alternator. Is it fine? How you have to consider different losses? Let us look at another problem based on losses. It is saying a 415 volt 3-phase delta connected synchronous motor runs at rated voltage with an excitation of 500 volt. Now remember, this is delta connected, which means line voltage is equal to phase voltage, which means the phase voltage is now 415 volt, EMF is 500 volt. Synchronous impedance is 0.5 plus J2. Friction, windage and iron losses are 1000 watt. So ZS is 0.5 plus J2 ohms. This comes out to be 2.061 at an angle of 75.963 degree ohm. Now we have to find the maximum shaft power output. Now since the friction losses are constant, maximum output power can also be corresponding to the maximum developed power, because as we saw in synchronous motor power flow diagram, shaft power will be developed power minus rotational losses. So maximum shaft power is corresponding to maximum developed power if rotational losses are constant. So what is the expression for developed power in a synchronous motor? 3 EF Vt by mod Zs cos of delta minus theta s minus 3 EF square by mod Zs cos of theta s. Okay, that is the formula. Now to maximize this developed power, what you should take? Delta must be equal to theta s. Theta s is basically angle of impedance and delta is the power angle. So what is P max? 3, let us take out common. EF can be also taken common. Zs, which is 2.061, can be taken common. So first one is Vt 415 minus EF into cos of theta s. Theta s we just now derived 75.963. So this power comes out to be 213.75 kilowatt. Okay. Now we know the friction and the iron losses are 1 kilowatt, which means shaft power will be 212.75 kilowatt. I have just subtracted 1 kilowatt corresponding to the losses, which gives me the total shaft power output. So remember this thing, whenever you are dealing with a synchronous machine question, please carefully look at whether the machine is star connected or delta connected. That will immensely help you in finding the solution. Next type of problems are based on voltage regulation. In voltage regulation, do not use the method that we use for transformer, which is I into r cos phi plus x sin phi. This method should not be used in case of synchronous machine. Why? Because it is an approximate method, and this approximation will deviate by a large amount as compared to actual result for the case of synchronous machine. So what should we do to find the voltage regulation? Find out magnitude of EMF minus mod V by mod V. This I told you in the previous video that what you can do. For mod E, you can use direct equation. What was that? V cos phi plus IARA whole square plus V sin phi plus minus IA XS square under root. Okay. Plus was for lagging and minus was for leading. Is it fine? So that is how you can calculate magnitude of EMF. And then we have to remember the condition for maximum voltage regulation. For maximum voltage regulation, theta must be equal to phi, and for zero voltage regulation, cos of theta plus phi is equal to minus IAZS by 2V phase. Okay. These two conditions you should always remember for the case of voltage regulation. Now let us see the problem. Determine the voltage regulation of a 2000 volt single phase. When you see this single phase, it means we do not have to use any factor of √3. Giving a current of 100 ampere at 0.8 power factor leading, and from the test result, field current of 100 ampere is produced by full load current 100 ampere is produced on short circuit by a field excitation of 2.5 ampere, which means short circuit current is 100 ampere. EMF of 500 volt is produced by on open circuit by same excitation. EOC is 500. From here I can calculate ZS. 500 by 100. There will be no factor of √3. It is single phase alternator. 5 ohm. Now armature resistance is 0.8. We can calculate XS under root 5 square minus 0.8 square, which will come out to be how much? 4.9356. Now the next step is to calculate the EMF in order to determine the voltage regulation. So if you want to calculate by phasor, it shall be 2000. Current is 100 ampere at 0.8 power factor leading. 0.8 corresponds to an angle of 36.86 into ZS, which is 0.8 plus J. Sorry, this will be ohm. 4.9356. Okay. This comes out to be 1822.57 at an angle of 14.06 degree volt. Now we have to find the voltage regulation. It will be 1822.57 minus 2000 by 2000 into 100%. So this comes out to be minus 8.87%. Okay. So as you can see, for a leading load, usually the voltage regulation comes out to be negative. In the next type of problem, it is based on droop characteristics. What is meant by droop characteristic is when you increase the load on any alternator, its speed and the frequency of output will decrease. Usually we assume that the frequency decreases linearly with power like this. So this is our no load frequency. This is our full load frequency corresponding to full load power output. Now here you have to remember the power output of any machine is equal to no load frequency minus actual frequency, no load frequency minus full load frequency into full load power output. This is the straight line equation governing the droop characteristics. And what is droop actually? It is no load frequency minus full load by full load into 100%. Similarly, in the denominator, there can also be no load frequency, which you have to judge based on the question. So let us see the problem. Two generators rated 500 and 600 megawatt are operating in parallel. The droop characteristics of their governor are 4% and 5% from no load to full load, assuming generators are operating at 60 Hz at no load, which means no load frequency is 60 Hz. So what is full load frequency of first one? It has a droop of 4%, 0.96 into 60, 57.6 Hertz. What about second one? It has a droop of 5%, so it will be 0.95 into 60, which is 57 Hertz. Now I can form the equation for power no load minus F upon no load minus full load, which is 2.4 into P full load. P full load of first alternator is 500. Similarly, P2 no load minus F by no load minus full load into P2 or P full load 2 is 600. Now it is saying a load of 1100 megawatt is shared by the alternators, which means P1 plus P2 is 1100. So now what you have to do is you have to substitute the values of P1 and P2 into this equation. Now both values are derived in terms of F, so we can calculate F. It will come out to be 57.3 Hertz. From there we can calculate P1 561.2 megawatt and P2 538.8. So that is how the load will be shared among the two generators. So for this you only have to remember the equation for power in terms of frequency. The method is always same. Express power in terms of frequency. Add both powers equal to the load power, that will give you frequency. From frequency we can determine the power of each generator. The next category of problem is based on synchronous motor, which is cylindrical rotor. Till now we were discussing about only alternator. Okay. Now in synchronous motor, what does change? In synchronous motor, the equivalent circuit essentially remains same. Like this. This is EF, VT, but here IA is going inwards. So here EF is VT minus IA into ZS. Okay. So similarly, if you want to write the magnitude of EMF, it will be V cos phi minus IARA square plus V sin phi minus plus IAXS का square. Okay, minus for lagging and plus for leading. So that is how you can determine the magnitude of EMF in case of a synchronous motor. Is it fine? Minus here corresponds to lagging, plus for leading. Otherwise, if you remember the formula for alternator, what to do is replace IA by minus of IA, and then you can get the same expression. Because everywhere there was plus, it will become minus. That way also you can derive this expression. Okay. The power expressions will remain same. So let us see. And the other thing that you have to remember is here the power angle delta is negative. Okay. It is saying a 1000 kilowatt 3-phase star connected 3.3 kV, which means phase voltage is 3300 by root 3. 24 pole 50 Hz synchronous motor has synchronous reactance of 3.24 ohm per phase. The resistance is 0. The motor is fed from infinite bus bars at 3.3 kV, which means per phase voltage is 3300 by root 3. Its field excitation is adjusted for unity power factor operation, which means phi is 0. Calculate the maximum power that the motor can deliver with excitation remaining constant. So, for excitation to be constant, first what we must know is what is the excitation or what is the excitation EMF. If you have terminal voltage, to determine EMF, you need armature current. Okay. So, let us find out armature current at rated value because it is saying rated load. So, what is the armature current under rated condition? 1000 kilowatt by root 3 into VL into cos phi. Cos phi is 1 because phi is 0 or unity power factor. So, here I am using P is equal to root 3 VLIL cos of phi. As you can see, the power given is in terms of real power. So, this current comes out to be 174.95 ampere. Once I have this, I can find out EMF. 3300 by root 3 minus 174.95. It has an angle of 0 into J 3.24. Okay, that will be my EMF. So, you have to calculate its magnitude, which will be under root 3300 by root 3 square plus 174.95 into 3.24 square. That way we can calculate the magnitude. Now I have already told you how to derive the maximum power output of a synchronous motor. P max is how much? It will be E V by XS, because here RA is 0. And if you are using both the line voltages, you need not have a factor of 3. But if you are using phase voltages, so it will be 3 E phase V phase upon XS if we have phase voltages. Okay. So, once you have E phase, we already know V phase is 3300 by root 3. We can calculate the maximum power output by substituting the values. Is it fine? So, that is how we calculate the maximum power or power in a synchronous motor. The next kind of problem based on synchronous motor is for power factor correction. Now, for power factor correction, what happens? We have a load originally which will have a certain real power and reactive power. Then we use synchronous motor. It will have certain synchronous real power and reactive power. Usually we take this as negative because we have to reduce the reactive power in order to improve the power factor. So, now the new apparent power is PL plus PSM plus J QL minus QSM. So, this we call as P2, this we call as P1. So, basically the objective is to find QSM. It will be P1 tan of phi 1 minus P2 tan of phi 2. This formula you always have to remember, and this PSM is the real power of synchronous motor. Now assume that this PSM was 0, that is synchronous motor does not consume any real power. Then what happens is this P1 will be same as the P2 because PSM will be 0. So it will become P times tan phi 1 minus tan of phi 2. That is case if the synchronous motor does not consume any real power. That is the only formula that you need to remember for the case of power factor improvement or the power factor correction. So see, it is saying an industrial plant takes a load of 5 megawatt. So load power is 5 megawatt and power factor is 0.8 lagging. From this I can form SL. It will be 5 plus J into 3.75. Okay. Based on this cos phi, I have calculated the reactive power. Now it is decided to replace one 500 kilowatt induction motor by a synchronous motor of same rating. Okay. Means this plant is taking a load of 5 megawatt. In that we have certain induction motors. Out of those induction motors, you are replacing one induction motor by a synchronous motor. So here power of induction motor and synchronous motor is same, which is 500 kilowatt. Now both have a efficiency of 90%. Now if efficiency is given, it is clear to me this is the output power, which means the input power can be derived by dividing it by efficiency. So it will be 555.55 kilowatt. That is the power input of the induction and the synchronous motor. Now induction motor operates at a power factor of 0.9 lagging, but synchronous motor at 0.8 leading, which means reactive power of induction motor will be 555.55 into tan of cos inverse 0.9, and it should be positive. Why? Because it is lagging power factor. So it is 269.067 kVAR. What about reactive power of synchronous motor? 555.55 into tan of cos inverse 0.8, and it will be negative because it is operating at leading power factor, minus 416.67 kVAR. Now what happens to the total load? In the total load, we are removing an induction motor, but we are adding a synchronous motor. Both have the same power, which means it will remain same as PL, which is 5 megawatt. What about reactive power? We are removing induction motor, but we are adding synchronous motor. So it was 3.75 minus 269, or if you keep it in MVAR, 0.269, and you are adding a synchronous motor, minus 0.416. Minus because there is a minus sign. So it becomes 3.065. Now we have the new real and the reactive power. We can calculate the new power factor. So you can calculate first phi, which is tan inverse QL dash by PL dash. Then cos of phi will come out to be 0.8526 lag. Why lag? Because this reactive power is positive. Okay. So that is how we can improve the power factor of any plant from 0.8 to 0.85 by the use of a synchronous motor. Is it fine? Moving on to the next type of problem. Till now we have been discussing about cylindrical rotor machine, but similarly we have another construction in synchronous machine, that is salient pole. So what is the difference in salient pole? The salient pole motors or generators do not have a uniform air gap across the rotor. They have one direct axis and they have one quadrature axis. The direct axis reactance is always greater than the quadrature axis reactance due to lesser air gap along the direct axis. So here what you need to remember is, first of all, the formula for tan of psi is the internal power factor angle, V sin phi plus minus IAXQ. by V cos phi plus IA RA. Plus is for lag, minus is for lead. Okay, this is for generator. For motor, what you will do? You will replace IA by minus IA. So what will happen? This will become minus plus, this will become minus. Okay, that is for motor. Now in generator and motor, what you have to remember? This psi is equal to delta plus phi. Okay. Now in generator, lagging, this one will be positive, this one will be positive, this one will be positive. Leading, this one will be positive, positive, negative. Okay. Similarly, motor, lagging, negative, negative, positive. Motor leading, negative, negative, negative. Okay. So remember, psi and delta will always have the same sign, and for generator it will be positive, for motor it will be negative. Phi will be positive for lagging, phi shall be negative for leading. Is it fine? So based on that, we can use direct formula for psi in terms of delta and phi. Now let us see this problem. It is a salient pole synchronous generator with negligible resistance and has the following per unit parameters. Here we need to calculate load angle and excitation EMF. Whenever RA is 0, you have to remember excitation EMF is V cos delta plus ID XD. Now what is this ID? Direct axis current, IA sin delta plus phi, or you can say IA into sine of psi. Okay. So now first let us calculate load angle, that is delta. For delta I need to find out psi. So tan of psi is V sin phi. Rated voltage 1 pu. Sine of phi, power factor is 0.8. So sine will be 0.6 plus IA. IA is how much? 1 pu, because rated kV or rated power into xq, it is 0.5 upon V cos phi 0.8 IA RA. RA is 0, so it can be neglected. So it will come out to be how much? 1.375. Okay. Now psi is equal to delta plus phi, where phi will be 36.86 and it will be taken as positive because it is lagging. So from here, if you calculate delta, it will be 17.1 degree. Now in order to calculate EMF, first we need ID. ID is 1 into sine of delta plus phi, yani 17.1 plus 36.86. Okay. So when you calculate EMF, it will be V into cos of delta, V into cos of 17.1 plus ID means sine of 53.96 into XD, which is 0.8. So this comes out to be 1.602 pu. So these equations you have to remember, one for the internal power factor angle and other for the induced EMF. The next problem is again based on salient pole machine, but now it is salient pole synchronous motor. Okay, and it is asking us the power angle. So let me again apply the same formula. Tan psi, but it is motor, so I will reverse IA. It will be V sin phi minus IA xq by V cos phi minus IA into RA. Okay. So what happens now? The armature current is not given to us. So we have to find armature current at full load. So full load is 50 into 10 to the power 6 by root 3 into 13.8. So this armature current comes out to be 2091.85 ampere. Now remember, in this formula, whenever you put the voltage, it must be phase voltage, which is 13,800 by root 3 into sine phi will be 0.6 minus 2091.85. XQ will be how much? 1.31 by 13,800 by root 3 into 0.8. Armature resistance is neglected, so second term in denominator is 0. So this comes out to be 0.32. Now for motor we know psi is equal to delta plus phi. But we all know delta is negative for motor, psi is negative, and phi will be positive because it is lagging. So delta will be how much? It will be phi plus psi. Okay. 1 minute. Psi will be taken as negative. So psi is coming out to be positive. Delta is negative for a motor. So it will be delta minus, phi minus psi. Phi is how much? 36.86. And psi is how much? Tan inverse 0.32, which is 17.7. So it will be 19.1. But we know for a motor, delta should always be negative. So when you write down in examination, you will write minus 19.1 degree. Because for motor, delta must always be negative. Is it fine? In the next one, it is again based on salient pole machine, but now it is talking about power. So for power, you should always remember the formula. If armature resistance is neglected, it is EV by XD sine of delta plus Vt square by 2 1 by XQ minus 1 by XD sine of 2 delta. Okay. Now in this case, again if you use line voltages, you will get 3-phase power. But for phase voltage, you will get a single phase power. Okay. And the next thing is there. This is called as electromagnetic power, and this power is called as reluctance power. Somehow if you wish to derive the power, maximum power or condition for maximum power, do not remember any direct formula. You have to differentiate this power with respect to delta and equate it to 0. That will give you the condition for maximum power. The next thing that you have to remember is, if you add any reactance or any impedance in series with the machine, it will equally be added in direct axis and synchronous axis, quadrature axis. See, in this case, the generator is connected to an infinite bus through a reactance of 0.2 pu. This is my external reactance. Excitation voltage is 1.3 pu. Infinite bus voltage is 1 pu. Direct axis reactance is 0.95. But due to external reactance, it will be 1.15. Similarly, quadrature is 0.7, but due to external, it will be 0.9. What is the active power supplied to the bus? We just need to plug in the values into this expression. 1.3, infinite bus voltage 1 pu, XD is 1.15, sine of delta, that is sine of 25, minus Vt square by 2, 1 by XQ minus 1 by XD, sine 2 delta is sine of 50 degree. So this will come out to be 0.57 pu. Okay. So that is how you calculate the active power delivered by a salient pole machine. Moving to the last problem based on Salient pole machine. It is based on slip test in which we determine the direct and the quadrature axis reactance. For slip test, you should always remember xd is equal to Vmax upon Imin and xq is Vmin upon Imax. So xd is how much? Maximum voltage is 108, minimum current is 10. So 10.8 ohm. xq is minimum voltage 96, maximum current 12, that is 8 ohm. So that is how we can calculate two reactances of a synchronous machine, that is direct axis and quadrature axis. Okay. So these are the type of problems that can be asked overall in case of a synchronous machine.